So in this video, what I want to try to do is I want to try to clear up the misconceptions about removable and non-removable discontinuities. I've chosen a couple problems from out of section 1.4 to take a look at here, and we're going to do problems 13 and 14. And if you read the directions, we want to find all discontinuities, and then for any discontinuity that is removable, we want to define a new function that removes that discontinuity. So with this function that's given in number 13, we aren't going to have to really worry about the limit not existing in a certain place unless it happens at an asymptote, because this function is not a piecewise function. We're not going to have one piece of the function leave off in a location that's different from where the next piece of the function picks up, because this is not a piecewise function that we're looking at in number 13. So what we're going to need to do is we're going to need to figure out when this function is undefined, and this function is undefined when the denominator is equal to 0. So if you set the denominator equal to 0, and then you try to solve this by factoring, if I factor it as a difference of squares, the value of x that makes this factor equal to 0 would be x equals -1, and the value of x that makes this factor equal to 0 would be x equals 1. What I can conclude right now is that my function is discontinuous at x equals plus or minus 1. The reason why we know our function is discontinuous at +1 and at -1 is because the function is undefined at those locations. This function is discontinuous at these two values. If all the directions said were to find the discontinuities of f of x, we'd be done. It says to try and figure out if these discontinuities are removable though. So this is something that we've been struggling with a little bit. What we need to try and decide now is whether or not we have a hole poked out of the graph at either or both of these x values, or an asymptote at either or both of these x values. And to determine that, what we're going to do is we're going to check a couple limits. So I want to check the limit as x approaches 1 on this function. And if you check the limit as x approaches 1 on the function, you're going to simply be trying to put 1 in place of this x and 1 in place of this x. And when you do that, you end up with a 0 in the numerator, you end up with a 0 in the denominator, so that's one of our indeterminate forms. When this happens to us, we need to do a little bit of algebra that hopefully lets us get past the indeterminate form. So I'm going to reevaluate the limit as x approaches 1, but the algebra that I'm going to do as I rewrite the limit is I'm going to factor this denominator. So the top is just going to stay as x minus 1, but in this denominator, what I'm going to be able to do is I'm going to be able to factor it as a difference of squares, and it's going to become an x plus 1 times an x minus 1. Now that the denominator is written as multiplication, since I have this factor of x minus 1 already in the numerator, I can cancel it with the factor of x minus 1 in the denominator. I end up with a 1 in the top and an x plus 1 in the bottom. If I put 1 in place of the x that remains, what I end up with is I end up with 1 over 1 plus 1, or 1 over 2. What this indicates is that as x approaches 1 on the graph of this function, whatever it might look like, the y value that you approach is 1/2 from either side. So we don't have an asymptote on this graph at x equals 1. We actually have a hole poked out of it at 1, 1/2. The fact that this limit was finite, it was not infinity or negative infinity, tells us that this is a discontinuity that can be removed. Before we actually remove it though, we'll go ahead and we'll make sure that we don't have a discontinuity at the other value of x. So if we check the limit as x approaches the other value where we know our function has an issue, -1, I want to try to put -1 in place of all my x's, and when I put -1 in place of this x and subtract 1, I get -2 in the numerator, and then in my denominator, -1 squared is +1, -1 gets me to 0. This is going to either be infinity or negative infinity. If we broke and checked one-sided limits, -1 from the bigger side, -1 from the smaller side, we'd be able to determine if it was infinity or negative infinity on either side of this x value. But the fact that this is not indeterminate, the fact that this is going to be an infinite value is enough to say that this is the location of a vertical asymptote and not the location of a hole poked out of the graph like we got back here in the initial limit that we checked. So we have a removable discontinuity at x equals 1. If we wanted to actually remove the discontinuity, I'm going to redefine the function. So I'm going to have this new function g of x, and the way that I'm going to define this new function g of x is in a piecewise fashion. I'm going to leave the function definition the exact same for all the values of x except at the location where I'm trying to fill in the open circle in the graph. So I have the same function definition for all x's that are not equal to 1. And then when x equals 1, I need to have a point on my graph that fills in the open circle at 1 comma 1/2. So I'm going to define the function to have a constant value of 1/2 at 1, and what we've done is we've redefined the function to remove the discontinuity. So this function, f of x, has two discontinuities, x equals -1, x equals +1. At x equals -1, we're going to have an asymptote as indicated by the fact that this is going to be an infinite value for the limit, and at x equals 1, we had a finite value for the limit, meaning we have a hole poked out of the graph and not an asymptote. So one removable discontinuity, one non-removable discontinuity. If we go on and discuss problem number 14 for a few minutes, it's in the same section of problems. We want to take the same approach. Again, it's not a piecewise function. We don't have to worry about this function having any places where the limit doesn't exist unless it happens at an asymptote. And if it happens at an asymptote, the function has to be undefined there. So what I want to do is I want to figure out when this function is undefined. And this function is undefined when the denominator is 0. So if we set the denominator equal to 0, and what I'm doing as I set the denominator equal to 0 is I'm trying to factor it. So if I factor this denominator, let's see, I guess I need two things that multiply together to give me -2 and that add together to give me +1. So I think if I go +1 and or +2, excuse me, and -1, I've got the factored form of this denominator now. X equals -2 makes the initial factor 0, and x equals 1 makes the second factor 0. So what we can say right now is that our function is discontinuous at these two values, x equals -2 and x equals 1. If we want to try to classify one of these discontinuities as removable, what we're going to need to do is we're going to need to check the limit as we approach each of those values. And if we get an infinite value, it tells us that we have an asymptote at either or both of these locations. If we get a finite value, a real number, it's going to tell us we have a hole poked out at whatever x value, comma, whatever the limit equals. So we'll check -2 first. So the limit as we approach -2, I'm going to plug -2 in place of all my x's. So if I put -2 in place of that x, I'm going to end up with a -8 in my numerator. So as I approach -2 on the graph of f of x, my numerator is getting closer and closer to -8. In my denominator, well, we know what's going to happen with the denominator when we put -2 in. We're going to end up with 0. That's why we listed it as a place where the function was discontinuous or where the function was undefined. So you can try to put -2 in again, but you're just going to get the same thing. You're going to get 0. This is not an indeterminate form. This is an undefined form, and if we wanted to figure out if the answer to this quotient was infinity or negative infinity, we'd have to check the limits on each side of -2. It will be infinity or negative infinity, therefore we know we have an asymptote at -2 and not a hole that's poked out of the graph there. So we don't have a removable discontinuity at this x value. Do we have a removable discontinuity at the other x value? So check the limit as you approach that x value. And if you check that limit, put 1 in place of the x in the numerator and you end up with 4 times 1, or 4. Put 1 in place of the x's in the denominator, and the same thing is going to happen here as what we discussed with -2. You're going to get 0. +1 makes the denominator 0. That's why we said we're discontinuous there. This is not an indeterminate form. It's not 0 over 0. This is an undefined form, meaning our answer is either infinity or negative infinity. To see which, we'd have to check one-sided limits on either side of +1. Because we know we're going to get infinity or negative infinity on either side of 1 and not a finite value, we can say that we have an asymptote at 1 as well. These x values, -2 and 1, are locations of asymptotes and not locations of holes poked out of graphs. If I click back to 13 here for a second, honestly, there are very few discontinuities that are removable, but a discontinuity will be removable if the function is undefined at that x value, like this function was undefined at 1, and the limit as you approach 1 is finite. That's what we got here. When we remove the discontinuity, we just redefined the function at a single point to fill the open circle in the graph in that was at 1, 1/2. So hopefully this helped out. As always, please see me if you have any questions.